On all scales in the universe, from our local neighborhood to the interstellar medium to individual galaxies to clusters to filaments and the great cosmic web, everything we observe appears to be made out of normal matter and not antimatter. This is an unexplained mystery. Image credit NASA, ESA, and the Hubble Heritage Teams to Strara. When you look out at the vastness of the universe, at the planets, stars, galaxies, and all there is out there, one obvious question screams for an explanation: why is there something instead of nothing? The problem gets even worse when you consider the laws of physics governing our universe, which appear to be completely symmetric between matter and antimatter. Yet as we look at what's out there, we find that all the stars and galaxies we see are made 100% of matter, with scarcely any antimatter at all. Clearly, we exist, as do the stars and galaxies we see, so something must have created more matter than antimatter, making the universe we know possible. But how did it happen? It's one of the universe's greatest mysteries, but one that we're closer than ever to solving. The matter and energy content in the universe at the present time left and at earlier times right. Note the presence of dark energy, dark matter, and the prevalence of normal matter over antimatter, which is so minute it does not contribute at any of the times shown. Image credit NASA, modified by Wikimedia Commons user, modified further by E. Siegel. Consider these two facts about the universe, and how contradictory they are. Every interaction between particles that we've ever observed, at all energies, has never created or destroyed a single particle of matter without also creating or destroying an equal number of antimatter particles. When we look out at the universe, at all the stars, galaxies, gas clouds, clusters, superclusters and largest-scale structures everywhere, everything appears to be made of matter and not antimatter. It seems like an impossibility. On one hand, there is no known way, given the particles and their interactions in the universe, to make more matter than antimatter. On the other hand, everything we see is definitely made of matter and not antimatter. Here's how we know. The production of matter-antimatter pairs left from pure energy is a completely reversible reaction, right, with matter-antimatter annihilating back to pure energy. This creation and annihilation process, which obeys EMC², is the only known way to create and destroy matter or antimatter. Image credit Dmitry Pogosyan, University of Alberta. Whenever and wherever antimatter and matter meet in the universe, there's a fantastic outburst of energy due to particle-antiparticle annihilation. We actually observe this annihilation in some locations, but only around hyperenergetic sources that produce matter and antimatter in equal amounts, like around massive black holes. When the antimatter runs into matter in the universe, it produces gamma rays of very specific frequencies, which we can then detect. The interstellar and intergalactic medium is of material, and the complete lack of these gamma rays is a strong signal that there aren't large amounts of antimatter particles flying around anywhere, since that matter-antimatter signature would show up. Whether in clusters, galaxies, our own stellar neighborhood or our solar system, we have tremendous, powerful limits on the fraction of antimatter in the universe. There can be no doubt everything in the universe is matter-dominated. Image credit Gary Steigman, 2008, via http://arxiv.org abs 0808.1122.in. Our own interstellar medium, the mean lifetime would be on the order of about 300 years, which is tiny compared to the age of our. This constraint tells us that, at least within the Milky Way, the amount of antimatter that's allowed to be mixed in with the matter we observe is at most 1 part in 1 quadrillion. On larger scales, of galaxies and clusters, for example, the constraints are less stringent but still very strong. With observations spanning from just a few million light-years away to over 3 billion light-years distant, we've observed a dearth of the X-rays and gamma rays we'd expect from matter-antimatter annihilation. What we've seen is that even on large cosmological scales, 99.999% of what exists in our universe is definitely matter like us and not antimatter. This is the Reflection Nebula IC 2631, as imaged by the MPG ESO 2.2 meters telescope. Whether within our own or between galaxies, there is simply no evidence of the gamma-ray signatures that would need to exist if there were significant pockets, stars, or galaxies made out of antimatter. Image credit ESO, so somehow, even though we aren't entirely sure how, we had to have created more matter than antimatter in the universe's past. Which is made even more confusing by the fact that the symmetry between matter and antimatter, in terms of particle physics, is even more explicit than you might think. For example, every time we create a quark, we also create an antiquark. Every time a quark is destroyed, an antiquark is also destroyed. Every time we create or destroy a lepton, we also create or destroy an antilepton from the same lepton family, and every time a quark or lepton experiences an interaction, collision or decay, the total net number of quarks and leptons at the end of the reaction, quarks minus antiquarks, leptons minus antileptons, is the same at the end as it was at the beginning. The only way we've ever made more or less matter in the universe has been to also make more or less antimatter in an equal amount. The particles and antiparticles of the Standard Model obey all sorts of conservation laws, but there are slight differences between the behavior of certain particle-antiparticle pairs that may be hints of the origin of baryogenesis. Image credit E. Siegel Beyond the Galaxy. But we know that it must be possible, the only question is how it happened. In the late 1960s, physicist Andrei Sakharov identified three conditions necessary for baryogenesis, or the creation of more baryons, protons and neutrons than antibaryons. They are as follows. The universe must be an out-of equilibrium system. It must exhibit C and CP violation. There must be baryon number violating interactions. The first one is easy, because an expanding, cooling universe with unstable particles and/or antiparticles in it is, by definition, out of equilibrium. The second one is easy, too, since C symmetry replacing particles with antiparticles and CP symmetry replacing particles with mirror-reflected antiparticles are both violated in the weak interactions. A normal meson spins counterclockwise about its north pole and then decays with an electron being emitted along the direction of the north pole. Applying C symmetry replaces the particles with antiparticles, which means we should have an antimeson spinning counterclockwise about its north pole decay by emitting a positron in the north direction. Similarly, symmetry flips what we see in our mirror. If particles and antiparticles do not behave exactly the same under C, P, or CP symmetries, that symmetry is said to be violated. Thus far, only the weak interaction violates any of the three. Image credit E. Siegel Beyond the Galaxy. That leaves the question of how to violate baryon number. In the Standard Model of particle physics, despite the observed conservation of baryon number, there isn't an explicit conservation law for either that a lepton number where a lepton is a particle like an electron or a neutrino. Instead, it's only the difference between baryons and leptons, B, L, that's conserved. So under the right circumstances, you can not only make extra protons, you can make the electrons you need to go with them. What those circumstances are is still a mystery, however. In the early stages of the universe, we expect equal amounts of matter and antimatter to exist, with very high speeds and energies. At the high temperatures achieved in the very young universe, not only can particles and photons be spontaneously created, given enough energy, but also antiparticles and unstable particles as well, resulting in a primordial particle and antiparticle soup. Image credit Brookhaven National Laboratory. As the universe expands and cools, unstable particles, once created in great abundance, will decay. If the right conditions are met, they can lead to an excess of matter over antimatter, even where there was none initially. There are three leading possibilities for how this excess of matter over antimatter could have emerged. New physics at the electroweak scale could greatly enhances the amount of C and CP violation in the universe, leading to an asymmetry between matter and antimatter. Sphaleron interactions, which violate B and L individually but conserve B, L, can then generate the right amounts of baryons in leptons. This could occur either without supersymmetry or with supersymmetry, depending on the mechanism. New neutrino physics at high energies, of which we have a tremendous hint, could create a fundamental lepton asymmetry early on leptogenesis. The sphalerons, which conserve B, L, would then use that lepton asymmetry to generate a baryon asymmetry. Or gut-scale baryogenesis, where new physics and new particles are found to exist at the grand unification scale, where the electroweak force unifies with the strong force. These scenarios all have some elements in common, so let's walk through the last one, just as an example, to see what could have happened. In addition to the other particles in the universe, if the idea of a grand unified theory applies to our universe, there will be additional superheavy bosons, X and Y particles, along with their antiparticles, shown with their appropriate charges amidst the hot sea of other particles in the early universe. Image credit E. Siegel Beyond the Galaxy. If ground unification is true, then there ought to be new, super-heavy particles, called X and Y, which have both baryon-like and lepton-like properties. There also ought to be their antimatter counterparts antiX and anti-E, with the opposite B, L numbers and the opposite charges, but the same mass and lifetime. These particle-antiparticle pairs can be created in great abundance at high enough energies, and then will decay at later times. So your universe can be filled with them, and then they'll decay. If you have C and CP violation, however, then it's possible that there are slight differences between how the particles and antiparticles XY versus antiX anti-decay. If we allow X and Y particles to decay into the quarks and lepton combinations shown, their antiparticle counterparts will decay into the respective antiparticle combinations. But if CP is violated, the decay pathways, or the percentage of particles decaying one way versus another, can be different for the X and Y particles compared to the antiX and anti-E particles, resulting in a net production of baryons over antibaryons and leptons over antileptons. Image credit E. Siegel Beyond the Galaxy. If your X particle has two pathways decaying into two up quarks or an anti-down quark and a positrons, then the antiX has to have two corresponding pathways, two anti-up quarks or a down quark and an electron. Notice that the X has B, L of 2/3 in both cases, while the antiX has negative 2/3. It's similar for the antiparticles. But there is one important difference that's allowed with C and CP violation. The X could be more likely to decay into two up quarks than the antiX is to decay into two anti-up quarks, while the antiX could be more likely to decay into a down quark and an electron than the X is to decay into an anti-down quark and a positron. If you have enough xantics and yanti pairs, and they decay in this allowed fashion, you can easily make an excess of baryons over antibaryons and leptons over antileptons where there was none previously. If the particles decayed away according to the mechanism described above, we would be left with an excess of quarks over antiquarks and leptons over antileptons after all the unstable, super-heavy particles decayed away. After the excess particle-antiparticle pairs annihilated away matched up with dotted red lines, we would be left with an excess of up and down quarks, which compose protons and neutrons in combinations of up-up-down and up-down-down, respectively, and electrons, which will match the protons in number. Image credit E. Siegel Beyond the Galaxy. In other words, you can start with a completely symmetric universe, one that obeys all the known laws of physics and that spontaneously creates matter and antimatter only in equal and opposite pairs, and wind up with an excess of matter over antimatter in the end. We have multiple possible pathways to success, but it's very likely that nature only needed one of them to give us our universe. The fact that we exist and are made of matter is indisputable. The question of why our universe contains something matter instead of nothing from an equal mix of matter and antimatter is one that must have an answer. This century, advances in precision electroweak testing, collider technology, and experiments probing particle physics beyond the standard model may reveal exactly how it happened. And when it does, one of the greatest mysteries in all of existence will finally have a solution.